आत्ता यायला भावा
इथं
हे काय ग्रीन हे वाले. कुठे तो ऑप्शन मेन करायचं नाही थांब पहिलं मला पाठव. आता बफर स्पीड विचारलं होतं तिथं.
नेट चालू आहे आपलं बफर स्पीड कसं
व्हिडिओ बफर होतं.
बोला
चालू आहे का? हॅलो येतोय? कॅन यू हिअर मी? कोणाला पाठवायचं आता? हॅलो गुड मॉर्निंग.
काय
झालं?
I, green. Eigenvalues and eigenvectors. Hello, friends. Good morning. Yesterday we have started eigenvalues and eigenvectors.
L.
Join होतात.
Yes.
Hello, we start now. Yesterday we have studied regarding how to find the eigenvalues. Then we have seen some properties for eigenvalues. Properties of eigenvalues. First property, sum of eigenvalues is equal to the sum of elements of principal diagonal, and that sum of principal diagonal also known as trace of the matrix, we can say. Then also we have seen how to find the eigenvalues. To find eigenvalues, we require a square matrix. You know very well. For any square matrix, first we have to write a characteristic equation. And characteristic equation, we have to write the determinant of A minus lambda I equal to 0. After writing determinant of A minus lambda I equal to 0, we need to expand this determinant. After expanding the determinant, we get some equation, and that equation is characteristic equation. In descending powers of lambda, we will get. If we have 3 by 3 matrix, we will get their third degree polynomial, third degree equation. It means we get the 3 roots there, and those 3 roots are nothing but eigenvalues. Also we call it as characteristic roots. Also we say proper values. Also we say the latent roots. So already we have seen some examples yesterday. And after finding eigenvalues, we have started yesterday eigenvectors. Without knowing eigenvalues, we cannot find the eigenvectors. Eigenvectors are dependent on the eigenvalues. So again, some properties yesterday we have seen. You see here, properties of eigenvectors. Again, we revise. The eigenvector x of a matrix A is not unique. Means eigenvectors are not unique. We may get different eigenvector, number of eigenvectors. Then second property we have seen yesterday, if lambda 1 comma lambda 2 comma so on lambda n be distinct eigenvalues of an n by n matrix, then corresponding eigenvectors x1, x2, so on xn form a linearly independent set. Third property, if two or more eigenvalues are equal, it may or may not be possible to get linearly independent eigenvectors corresponding to the equal roots. Fourth property, two eigenvectors x1 and x2 are called orthogonal if x1 transpose x2 equal to 0, means product of these two vectors. One vector, we have to find transpose of that vector x1 transpose x2 equal to 0. And fifth property, eigenvectors of a symmetric matrix corresponding to different eigenvalues are orthogonal. So as we discussed yesterday, I told we are going to find eigenvectors, eigenvalues and eigenvectors for symmetric matrix as well as for non-symmetric matrix. There will be four cases. First case is non-symmetric matrix with repeated roots, repeated eigenvalues. Non-symmetric matrix with different eigenvalues. Third case is symmetric matrix with different roots. And last case is symmetric matrix with repeated roots, repeated eigenvalues. So yesterday we were here orthogonal vectors. You know which vectors are said to be orthogonal. Two vectors x and y are said to be orthogonal if x1 transpose x2 equal to x2 transpose x1 equal to 0. So one example is here. Determine whether the eigenvectors of the matrix A are orthogonal. Here you see matrix A is given matrix 1 0 minus 1 1 2 1 2 2 3. So as we discussed yesterday, for a given matrix, you write let A equal to this matrix. Then after writing, we have to write there so that the characteristic equation determinant of A minus lambda I equal to 0. And for this matrix, the determinant of A minus lambda I is written here. So this determinant 1 minus lambda 0 minus 1 1 2 minus lambda 1 2 2 3 minus lambda, this determinant equal to 0. So we can expand this determinant 1 minus lambda into minor of this 1 minus lambda, which is 2 minus lambda into 3 minus lambda minus 2. Then minus 0. Then minus 1 into 2 minus 2 into 2 minus lambda. So after simplification of this, you will get lambda minus 1 into lambda square minus 5 lambda plus 6 equal to 0. So this is a polynomial of degree 3 in lambda. So you will get here 3 eigenvalues lambda equal to 1, comma 2, comma 3 are three distinct eigenvalues for the matrix A. Then to find the eigenvectors, we need to write Ax equal to 0. A is A minus lambda I into x equal to 0. So which is written here, A minus lambda I, which is matrix. X is vectors, x1, x2, x3. You can write 3 variables, 3 by 3 matrix is there. So you can write Ax equal to 0. Matrix A minus lambda I into x equal to 0 matrix. So first eigenvalue we have lambda equal to 1. You can see here. So 1 minus lambda, 0 minus 1, 1, 2 minus lambda, 1, 2, 2, 3 minus lambda. This matrix A minus lambda I into x. X is, you can write 3 by 3 matrix, 3 vectors x1, x2, x3 equal to 0 matrix, 0, 0, 0. Column matrix you can write. So first eigenvalue is lambda equal to 1. So just you put lambda equal to 1. You will get 1 minus 1, 0 minus 1, 1, 2 minus lambda, put lambda equal to 1, which is 2 minus 1, 1. Then last row, 2, 2, 3 minus lambda, replace lambda by 1, 2, 2, 3 minus 1 into column matrix x1, x2, x3 equal to 0 matrix, 0, 0, 0. So this gives 0, 0 minus 1 matrix, 1, 1, 1 and 2, 2, 2 matrix into x equal to 0. Now from this, you will get x1 plus x2 plus x3 equal to 0. Three equations. And from first row, 0x1 plus 0x2 minus x3 equal to 0. Meaning is that x3 equal to 0 and x2 equal to minus x3 minus x1. x3 is 0. So x2 equal to minus x1. If we put x1 equal to k, you will get x2 equal to minus k. Zero minus k, which is x2 equal to minus k. It means your first eigenvector x1 equal to k minus k 0, or it may be written x1 equal to k, you take k outside, 1 minus 1 0. So first eigenvector x1 equal to 1 minus 1 0. Now similarly put your second eigenvalue is 2, put lambda equal to 2. Here you put lambda equal to 2, you will get then you can find second eigenvector x2, put lambda equal to 2 in matrix A minus lambda I into x equal to 0. You will get one system of equations. Here you see, you will get here two different equations. First two equations are same, but last two equations are different. Now you choose different two equations, and by using Cramer's rule, these last two equations, x1 plus 0, x2 plus x3 equal to 0, and last equation 2x1 plus 2x2 plus x3 equal to 0. We need to use Cramer's rule here. x1 divided by, you take determinant of other coefficients, x2 0 1 2 1. So 0 minus 2, x1 by 0 minus 2 equal to minus x2 upon, delete that coefficients for x2 and you take determinant of others, that is 1 1 2 1, 1 1 2 1, 1 minus 2. Here x2 by 2 minus 1 equal to x3. Other determinant x3 by 1 2 2 2. Sorry, 1 0 2 2 determinant. So x1 equal to, you will get minus 2 x2 is minus 1 and x3 is 2. So second eigenvector 2 minus 1 minus 2 you will get. Or you can write minus 2 1 2. You may write, no problem. x2 is minus 2 1 2. Now similarly we find for lambda equal to 3. If we put lambda equal to 3, you will get again three equations. All three equations are different here. Minus 2x1 plus 0x2 minus x3 equal to 0. Then x1 minus x2 plus x3 equal to 0. And last equation, x1 plus x2 plus 0, 2x1 plus 2x2 plus 0x3 equal to 0. So we choose again two different equations. So first two equations you can take again using Cramer's rule. X1 you will get k, x2 you will get minus k, and x3 you will get minus 2k. And third eigenvector is 1 minus 1 minus 2. 1 minus 1 minus 2. Now x1 transpose x2, your x1 is 1 minus 1 0 and x2 is 2 minus 1 minus 2. If we take x1 transpose, it will be row matrix, x2 is column matrix, so we can multiply row into column, you will get 3. x2 transpose x3, you will get 7, and x3 transpose x1, you will get 2. And what is our condition for orthogonal vectors? x1 x2, x1 transpose x2 equal to 0. It is the condition. x2 transpose x3 equal to 0. It is again condition for orthogonality. x3 transpose x1 equal to 0. It is again condition for orthogonality. But every product we are getting non-zero. So what it means? All the vectors are not orthogonal eigenvectors. This shows that there are three distinct eigenvectors. x1, x2, x3 are not orthogonal eigenvectors. Now this is just for sake of understanding orthogonal vectors, how to find orthogonality. We have to check the product for two different eigenvectors. Now this is the first case. We start with this non-symmetric matrices with repeated eigenvalues. So we start with direct example here. So we see 3 by 3 matrix. Here you see, find the eigenvalues and eigenvectors of matrix A. Matrix A is given 3, 1, 4, 0, 2, 6, 0, 0, 5. So for given matrix, we write so that characteristic equation determinant of A minus lambda I equal to 0. So after expanding this determinant, A minus lambda I, it will be 3 minus lambda 1, 4 in determinant, 0, 2 minus lambda 6, 0, 0, 5. You see, this is a non-symmetric matrix. So we need to expand this determinant. Expand this 3 minus lambda into 2 minus lambda into 5 minus lambda. Other is 0. So minus 1, 0, 0 means you will get only three parts here. 3 minus lambda into 2 minus lambda into 5 minus lambda. The characteristic equation, determinant of A minus lambda I equal to 0. So therefore 3 minus lambda into 2 minus lambda into 5 minus lambda equal to 0. So therefore the eigenvalues are lambda equal to 2, 3, 5. All the eigenvalues are different, which are 2, 3, 5. Now we find eigenvectors of the matrix A corresponding to the eigenvalue lambda is given by non-zero solution of the equation, which is matrix A minus lambda I into x equal to 0. Or for this we get a system of simultaneous linear equations as 1. You can write A minus lambda I into x equal to 0, which is 3 minus lambda 1, 4 matrix, which is a coefficient matrix. We can say 3 minus lambda 1, 4, 0, 2 minus lambda 6, 0, 0, 5 minus lambda is a coefficient matrix, and matrix of variables, which is x. Matrix is again 3 by 3. So you can write 3 vectors x1, x2, x3 equal to 0 matrix, which is 0, 0, 0. You can say it is equation number 1. Now your first eigenvalue is lambda equal to 2. So put this lambda equal to 2 in this system of equations. Lambda is 2, 3 minus 2, 1, 4, 0, 2 minus 2, 6, 0, 0, 5 minus 2. Then you will get 1, 1, 4 after using lambda equal to 2. 0, 0, 6 you will get. Then 0, 0, 3. So you will get again 2, 3 equations you will get. x1 plus x2 plus 4x3 equal to 0. Second equation will be 0x1 plus 0x2 plus 6x3. You will get 0. If we use the Cramer's rule, x1, x2, x3, you can see here, definitely x1 is 1, x2 is minus 1, x3 is 0. So therefore this equal to k. x1 is k, x2 is minus k, and x3 is 0. Means your first eigenvector x1 is k into 1 minus 1, 0. Already we know eigenvectors are not unique. So k may be anything. So your first eigenvector 1 minus 1, 0. Then put lambda equal to 3. The corresponding eigenvector, put lambda equal to 3. Again you will get the set of equations. 3 minus 3, 1, 4, 0, 2 minus 3, 6, 0, 0, 5 minus 3. Again simplify. And first two equations you can take, or maybe last two equations. So first two equations, 0x1 plus x2 plus 4x3 equal to 0. 0x1 minus x2 plus 6x3 equal to 0. Again, using Cramer's rule, you have x1 divided by determinant 1 4 minus 1 6. 6 minus minus plus 4 you will get x2 0 4 0 6, x3 by determinant 0 1 0 minus 1. So you'll get x2 is 0, x3 is 0, x1 is non-zero. x1 equal to 1 you can write. So x1 is the second eigenvector k00 or k times 100, which is the eigenvector corresponding to the eigenvalue lambda equal to 3. So similarly, we find lambda equal to 5 for lambda equal to 5. Put lambda equal to 5. Substitute lambda equal to 5. Again, you will get 3. Here last row is 0, 0, 0 you will get. So two equations, using two equations, minus 2x1 plus x2 plus 4x3 equal to 0. 0x1 minus 3x2 plus 6x3 equal to 0. Then again using Cramer's rule, you will get the third eigenvector k times 3 2 1. So your third eigenvector is 3 2 1. So therefore, if symmetric matrix with different roots, and we have used here Cramer's rule, we have substituted each eigenvalue in that system of equations, and every time we get different eigenvector here. Just Cramer's rule using, here are some examples are given. You can solve these examples. A symmetric matrix with different eigenvalues. You will get all the three eigenvectors are different for different eigenvalues. Now the second case, non-symmetric matrix with repeated eigenvalues. Procedure is same, only for repeated eigenvalues you have to choose another way to find eigenvector. It is simple, it is not difficult. So here is one example. Find the eigenvalues and eigenvectors of the matrix. Matrix is given 2 1 1 1 2 1 0 0 1. So to find eigenvectors, we write the determinant of A minus lambda I equal to 0, characteristic equation. After writing characteristic equation as determinant of A minus lambda I equal to 0, expand this determinant After expanding this determinant, you will get the values for lambda 1, 1, 3. And now you can see here two eigenvalues are similar, same eigenvalues means repeated roots are here, and third eigenvalue is different. If the roots are equal, the procedure is this. So first eigenvalue, you put lambda equal to 1 to find eigenvector. To find the eigenvector, we have to write non-zero equations, that is matrix A minus lambda I into x equal to 0. Again here matrix is 3 by 3. Put lambda equal to 1. You will get this 2 minus matrix 2 minus lambda 1 1 1 2 minus lambda 1 0 0 1 minus lambda into x equal to 0. Now we put lambda equal to 1. After substituting lambda equal to 1, you will get the system of equations ax equal to 0, that is coefficient matrix. You will get 1 1 1. Again you will get 1 1 1, and last will be 0 0 0. Means you will get one equation here, x plus y plus z equal to 0. X plus y plus z equal to 0. It means you will get two equations are similar here, x plus y plus z equal to 0. And last equation 0x1 plus 0x2 plus 0x3. Meaning is that no value is 0. 0x1 plus 0x2 plus 0x3 equal to 0. Now, if this situation arises, in that case, we have to choose x1 equal to k1 and y equal to k2 here. Here is variables are x, y, z. So replace x by k1, y by k2, and which implies z equal to minus k1 minus k2 you will get. Means k1 plus k2 plus z equal to 0. So you can if we choose k1 k1 is 1, k2 is 1, z equal to minus 2. If we choose k1 equal to k2, now you can take k1 k2. If these two are k1 equal to 1, k2 equal to 1, or if we choose k1 is 1, k2 is 0, you will get another value here. Here you see the second k1 is 1, k2 is 0. Therefore, z is minus 1 you will get there. It means second eigenvector 1, 0, minus 1. In first case, k1 equal to k2, which is 1. And in second case, for repeated roots, you choose k1 is 1, k2 is 0, or you can choose in first case also k2 is 0, k1 is 1, 1 and same. We know eigenvectors are not unique. So in this case, first eigenvector x1 is 1, 1 minus 2. For same eigenvalue, second eigenvector 1, 0 minus 1. This is the procedure. And we have to choose x equal to k1, y equal to k2, and z in terms of k1, k2 for the repeated roots. Then we have to choose the values of k1 and k2. Some either k1 is 0, k2 is 1, or k2 is 0, k1 is 1, or you can take 1, 1, both k1 is 1, k2 is 1, either same or different, 0, 1, 1, 0, or 1, 1. You may take anything from these. It means you will get different eigenvector for 2. Now, for third eigenvalue, lambda equal to 3. You may get two different equations for a different eigenvalue. First is put lambda equal to 3. It will be 2 minus 3, 1, 1, 1, 2 minus 3, 1, 0, 0, 1 minus 3 into x. X is x, y, z equal to 0 matrix 0, 0, 0, and which after using lambda equal to 3 you will get the coefficient matrix minus 1, 1, 1, 1 minus 1, 1, 0, 0, minus 2. First row minus 1, 1, 1. Second row 1 minus 1, 1. Then, so you find the third eigenvector. 3 equations you will get. Minus x plus y plus z equal to 0. You can use this operation. R2 changes to R2 plus R1. In row, all 1, 1, 1. So you may get some elements 0 using this operation. Means it will be again simple. Z equal to 0. X equal to y you will get. You can take k. Again here k0 you will get your third eigenvector. So first eigenvector 1, 0, minus 1, 1, 1, minus 2. We can write second eigenvector 1, 0, minus 1, and third eigenvector is 1, 1, 0. So again here similar example. Find all the eigenvalues and eigenvectors of the matrix. Matrix is given minus 2, 2, minus 3, 2, 1, minus 6, minus 1, minus 2, 0. Here we write characteristic equation as determinant of A minus lambda I equal to 0. If we write determinant of A minus lambda I equal to 0, you will get minus 2 minus lambda, 2 minus 3, 2, 1 minus lambda, minus 6, minus 1, minus 2, 0 minus lambda equal to 0. So after expanding this determinant, you have the characteristic equation in terms of lambda. You will get lambda cube plus lambda square minus 21 lambda minus 45 equal to 0. 3 by 3 matrix. We have here third degree polynomial, lambda cube plus lambda square minus 21 lambda minus 45 equal to 0. Again, yesterday I told one formula for this characteristic equation. If you remember, that is lambda cube minus s1 lambda square plus s2 lambda minus determinant of a equal to 0. This equation you can use, and you know what is s1. S1 is the trace, sum of elements in principal diagonal s1. S2, sum of minors of elements of principal diagonal, and determinant a, you know, you can find. So there are two ways to expand this determinant. First way, directly you expand this determinant. Second way, you write the equation lambda cube minus s1 lambda square plus s2 lambda minus determinant of a equal to 0. So after finding s1, s2 and determinant, you substitute values and you will get the equation. This lambda cube plus lambda square minus 21 lambda minus 45 equal to 0. So you need to use synthetic division method again to find the eigenvalues. Here you see, here given synthetic division method. Now we have to take the trial root. Lambda equal to minus 3 is taken here. Lambda equal to minus 3. Now you have to write the coefficients for that equation. Lambda cube plus lambda square minus 21 lambda minus 45 equal to 0. So coefficients 1, 1, minus 21, and constant is there minus 45. And if remainder is 0, we can say that is the one of the root for that equation. Here trial lambda equal to minus 3. Put lambda equal to minus 3 in this equation. Here already given here. Lambda is minus 3 cube, which is minus 27, plus lambda square. 3 square is plus 9, minus 21 into 3, minus 3, which is plus 63, minus 45. So minus 27 minus 45, 65, 72, and plus 72. 72 minus 72 equal to 0, meaning is that lambda plus 3 is one of the factors for that equation. So remaining factors you can find in this way. So remainder is 0. So lambda equal to minus 3 is one of the root. You take 1 as it is below. 1 into minus 3, you write in lambda square coefficient below -3, which is -2. -2 into -3, you write below -21, that is +6. -21 plus 6 is -15. So remainder is -15. So -15 into -3, you will get +45. Here is -45 plus 45, you will get 0. So lambda plus 3 into, you will get lambda square -2 lambda minus 15 equal to 0. So again simplify, you will get the roots 5 minus 3 minus 3. So therefore eigenvalues are 5 minus 3 minus 3. Eigenvalues are 5 minus 3 minus 3. So corresponding to each eigenvalue, we can find the eigenvectors. So we will consider the matrix equation here. Matrix A minus lambda I into X equal to 0. So first eigenvector, here you will get one system of equations, which is -2 minus lambda 2 minus 3, 2 1 minus lambda minus 6, -1 -2 minus lambda. This is matrix A minus lambda I into X vector x, y, z, 3 variables equal to 0, matrix 0, 0, 0. We have, this is a system of linear equations. So first root, put lambda equal to 5, first eigenvalue in this system. You will get -7x plus 2y minus 3z equal to 0. Then second equation, 2x minus 4y minus 6z equal to 0. Third equation, x plus 2y plus 5z equal to 0. It means all the three different equations you will get here in this set of equations. So we take first two equations. You can take first two, last two, and first and last. If all the three equations are different, you may choose any two equations and we can find the eigenvector. If only two are same, only two are different equations, you can take those two different equations. Here first two equations we choose. So find first two, -7x plus 2y minus 3z equal to 0. 2x minus 4y minus 6z equal to 0. So using Cramer's rule, you will get x equal to k, y equal to 2k, and z equal to -k. And therefore, your first eigenvector corresponding to eigenvalue lambda equal to 5. Eigenvector is 1, 2, -1, you can write. Similarly, for lambda equal to -3, using lambda equal to -3, you will get x plus 2y minus 3z equal to 0, 2x plus 4y minus 6z equal to 0, minus x minus 2y plus 3z equal to 0. It means, you see, all the three equations are same here, x plus 2y minus 3z. Second equation, 2 is common, x plus 2y minus 3z equal to 0. Third equation, minus is common there, x plus 2y minus 3z equal to 0. Means all three equations are same in this system. So if the roots are same, as in previous example, we choose x equal to k1, y equal to k2. Then from x plus 2y minus 3z equal to 0, this z will be 1 by 3 times k1 plus 2k2. Hence the eigenvector k1 k2 1 by 3 times k1 plus 2k2. So here we have to choose values of k1 and k2. You can take k1 is 0, k2 is 3, or k1 is 1, sorry, k1 is 0, k2 is 1 also you can take, no problem. If we take k1 is 0, k2 is 1, k1 is 0, k2 is 1, k1 0, k2 is 1, means you will get 0, 1, 2 by 3 you will get 0, 1, 2 by 3, and which is nothing but 0, 3, 2. You can write in this way also. If you have confusion, why we take k2 equal to 3? If k2 equal to 1, definitely that 3, 0, 1, 2 by 3 we are getting here. So that 3 will be transferred 0, 3, 2 you will get. This is second eigenvector. Again you choose k2 is k1 is 1, k2 is 0. You will get similar. K1 is 1, k2 is 0. K1 is 1, k2 is 0. K1 is 1, k2 is 0. 1 by 3 you will get. 1, 0, 1 by 3, which is nothing but 3, 0, 1. Third eigenvector. You see, if the symmetric matrix with repeated roots, if for repeated roots, if we put that repeated eigenvalues in that system of equations, definitely you will get three equations which are same. If equations are same, in case of symmetric matrix with repeated roots, we have to choose x equal to k1, y equal to k2, and definitely we will get z in terms of k1, k2. Then you choose first case k1 is 0, k2 equal to 1. In second case, choose k1 is 1, k2 is 0. You will get two different eigenvectors. You can remember this is the procedure for the case non-symmetric matrix with repeated roots. For different eigenvector, no doubt you can use their Cramer's rule. If the three equations are same for repeated roots, we will get a trivial solution there. Means you will get all the values for x, y, z, you will get 0 there. So this other way to choose, k1 is 1, k2 is 0, or k1 is 0, k2 is 1. In this way you can find the three eigenvectors here, as in this example we have chosen. So 3 eigenvectors, x1 is 1, 2, minus 1, x2 is 0, 3, 2, and x3 is 3, 0, 1. 3 eigenvectors. This is for symmetric matrix with repeated roots and symmetric matrix with different eigenvalues. Here is one exercise. Repeated roots. You can solve this. Now, symmetric matrix with non-repeated eigenvalues. This procedure is same. For non-repeated eigenvalues, you have to use here Cramer's rule again for non-repeated eigenvalues. Just we see one example here. Find the eigenvalues and the corresponding eigenvectors of the matrix -2, 5, 4, 5, 7, 5, 4, 5, -2. You see, this is a symmetric matrix. What is mean by symmetric matrix? Aij matrix Aij equal to minus Aji. A12 is 5, A21 is 5, A13 is 4, A31 is 4, A23 is 5, A32 is 5. Means this is a symmetric matrix. So similar procedure to find eigenvalues. We write characteristic equation, which is determinant of A minus lambda I equal to 0, which is -2 minus lambda in determinant, 5, 4, 5, 7 minus lambda, 5, 4, 5, -2 minus lambda, determinant A minus lambda I equal to 0. So after expansion, you will get this equation, lambda cube minus 3 lambda square minus 90 lambda minus 216 equal to 0. Again, using synthetic division method, you take the trial. You check different trials, lambda equal to -3. Here lambda equal to -3 is the first root, lambda minus 3 used here. Synthetic division method, coefficients are 1, -3, -90, along with constant -216. Then first constant coefficient is 1. So write 1 as it is. Your trial root is -3. So 1 into -3 is -3. Second coefficient -3 then -3 equal to -6. Then multiply with that trial root. -6 into -3 is +18. Your third coefficient is -90. So write below 18. -90 + 18 is -72. So minus 72 is the remainder again. So minus 72 into trial root, that is minus 3. It will be 216 plus 216. So constant is minus 216. Again we are getting plus 216. The addition is 0. So remainder is 0. So lambda equal to minus 3 is one of the root. Then you will get quadratic equation lambda square minus 6 lambda minus 72 equal to 0. Then using this quadratic equation, you may find again two roots, 72 here. Minus 12 plus 6 is minus 6. So minus 12 lambda plus 6 lambda. You can find the factors. Lambda minus 12 into lambda plus 6 equal to 0. So therefore, the eigenvalues are lambda equal to minus 3, minus 6 and 12. Three different eigenvalues we are getting for given symmetric matrix. Now matrix equation for eigenvectors, which is matrix A minus lambda I into X vector equal to 0 matrix. So you will get system of equations minus 2 minus lambda 5 4 5 7 minus lambda 5 4 5 minus 2 minus lambda into vector x, that is x y z column matrix equal to 0 matrix. So this is a system of equations. So we use three different eigenvalues. Put lambda equal to minus 3. You will get first two equations are different. Last two are again, last is also different. Three equations are different you will get. So using Cramer's rule, you can find first eigenvector as x1 equal to 1 minus 1 1. Similarly, you can find by using lambda equal to minus 6. Again you will get, here you see first and last equation is same, but second equation is different. So you can take first and second equation. You can find, put lambda equal to minus 6. You will get minus 2 minus lambda. You will get lambda equal to minus 6. 4 5 4 5 13 5 4 5 4. Means first and last row are same, but middle row is different. Means two different equations. First equation 4x plus 5y plus 4z equal to 0. Second equation 5x plus 13y plus 5z equal to 0. So using Cramer's rule, second eigenvector minus 1 0 1 you will get. And similarly for lambda equal to 12, you can write minus 2 minus lambda, which is minus 14, 5 4 5 minus 5 5 4 5 minus 14. All the three equations are different here. You can choose any two equations, and using Cramer's rule, you will get x is 1, y is 2, z is 1. So third eigenvector 1, 2, 1 means, again for a symmetric matrix with repeated roots, you will get three different eigenvalues, and by using Cramer's rule for each eigenvalue, you can find the three eigenvectors. Again here 1, 2, 4 symmetric matrix is given. Characteristic equation, determinant of A minus lambda I. 1, 2, 4 using Cramer's rule. You see here Cramer's rule is used. Here is some exercise. Now this last symmetric matrix with repeated eigenvalues. Here is 2 may be same, third is different, or all the three may be same. Here you see, find all the eigenvalues and eigenvectors of the matrix. Matrix is given 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. Characteristic equation, determinant of A minus lambda I equal to 0. Repeat the same procedure to find eigenvalues. After expanding this determinant, we have this characteristic equation, lambda cube minus 6 lambda square plus 9 lambda minus 4 equal to 0. We are dealing with symmetric matrix. So again, we may find eigenvalues. Again, by using synthetic division method, first eigenvalue lambda equal to 1, first factor lambda minus 1. Using synthetic division method, you may find lambda 1 into lambda square minus 5 lambda plus 4 equal to 0. And roots will be lambda equal to 1, 1, 4. Means two roots are equal and other is different. 1, 1, 4. So you may choose this way. Put lambda equal to 4 to find eigenvectors. The matrix equation is matrix A minus lambda I into x equal to 0. We have to write each and every step clearly. For lambda equal to 4, first for different eigenvalue, lambda equal to 4, you will get three different equations from the system. You may take any two equations. It is here. So put lambda equal to 4, 2 minus 4 minus 1, 1. Then it is minus 1, 2 minus 4 minus 1. Last row 1 minus 1, 2 minus 4. Then you will get the matrix minus 2 minus 1 1 -1, -2, -1, and 1, -1, -2. Then if you write in the form of equations, you will get all three equations are different. If all three are different or any two are different, you may choose here Cramer's rule. By using Cramer's rule, you can find first eigenvector for this different eigenvalue lambda equal to 4. 1 minus 1, 1 you will get. x1 is k, x2 is minus k, and x3 is k. This is for symmetric matrix with repeated roots, and among these roots one is different, lambda equal to 4, where we found here lambda equal to 4, eigenvector is 1 minus 1, 1. Now for similar roots, lambda equal to 1, for lambda equal to 1, this second eigenvector, as in previous case, symmetric matrix, non-symmetric matrix with repeated roots, you choose that same way, first way, x1 equal to k1, x2 equal to k2, and find second eigenvector. But for third eigenvector, the procedure is different. If the matrix is symmetric and roots are repeated, again put lambda equal to 1, you will get one equation, you will get only x1 minus x2 plus x3 equal to 0, and last two rows are 0, 0, 0. Definitely x1 is non-zero, x2 is non-zero, and x3 is non-zero. Your one equation, after substituting lambda equal to 1, x1 minus x2 plus x3 equal to 0. So let us choose x1 is k1, x2 is k2, and which implies x3 equal to k2 minus k1. So therefore, second eigenvector is x2, which is k1, k2, k2 minus k1, second eigenvector. And if we choose k1 equal to k2 equal to 1, or you may choose k1 is 0, k2 is 1, or you may choose k1 is 0, k2 is 1, or k2 is 0, k1 is 1. You can take any one. So here k1 equal to k2 equal to same. You can take 1, 1. So k2 minus k1, 1 minus 1, you will get 0. So second eigenvector is 1, 1, 0. Now you see there is one property for eigenvectors. For symmetric matrix, two different eigenvectors are orthogonal. Two different means first eigenvector we have found. Second eigenvector for lambda equal to 1, we have 1, 1, 0. It means these two eigenvectors are orthogonal. When using this property, now we can find the third eigenvector here. You see here, let x3 is eigenvector Lmn. Using that eigenvector property, as x3 is orthogonal to x1, since the given matrix is symmetric, it means we have to write Since the given matrix is symmetric, therefore x3 is orthogonal to x1 and x3 is orthogonal to x2. If x3 is orthogonal to x1, means x3 transpose x1 transpose x3 equal to 0. x1 transpose x3 equal to 0, and x2 transpose x3 equal to 0 using the property for symmetric matrix with first two different eigenvectors. Orthogonality property we can use. So x1 transpose x3, x1 is 1 minus 1 1, so you'll get x3 is LMN, x1 is 1 minus 1 1, you will get L minus M plus N equal to 0. Then x3 is orthogonal to x2. Matrix is symmetric, we know. So you'll get 1 1 0 row matrix transpose of that x2, which is 1 1 0, and x3 is LMN column matrix. So you'll get another equation, L plus M plus 0 N equal to 0. Again these two, L minus M plus N equal to 0 and L plus M plus 0 N equal to 0. We solve these two as a simultaneous linear equations. For L, M, N, we need to use again Cramer's rule, and you will get x3 is minus 1 1 2, minus 1 1 2. And the procedure is different for symmetric matrix with repeated roots. Symmetric matrix with repeated root, the first eigenvector you can find for different eigenvalue. Then second eigenvector for same eigenvalue, you adopt the same procedure as in non-symmetric matrix with repeated root. First, we have chosen there x equal to k1, x2 equal to k2, and find x3 in terms of k1, k2. Then we have chosen either k1 equal to k2 or k1 is 0, k2 is 1, or k2 is 0, k1 is 1. You can take any one from these three. Then find that second eigenvector. To find third eigenvector in case of symmetric matrix with repeated roots, we have to use that property. Eigenvectors are orthogonal in case of symmetric matrix. So same property, same concept, using orthogonality property, we can find the third eigenvector. It is essential. If the matrix is symmetric, you go in proper way to find third eigenvector. Orthogonality property is applicable here. So again, here is some exercise for symmetric matrix with repeated eigenvalues. So again, there are different examples are given here. You can see. If you have any queries, you can chat with me. If you have any queries, you can write in chat box. Do you have any queries? So if you are not having any query, so this is about eigenvalues and eigenvectors. We have discussed 4 cases. Yesterday we have discussed about eigenvalues, how to find the eigenvalues. I summarize in 1-2 minutes. To find eigenvalues, we require characteristic equation. For a given matrix A, we write the characteristic equation as determinant of A minus lambda I equal to 0. If 3 by 3 matrix is there, after expanding the determinant, we get the third degree polynomial. We get 3 roots, and these 3 roots are nothing but the eigenvalues. Then you have seen some properties of eigenvalues. Eigenvalue properties are whether our eigenvalues are same or not. We can check. If we take the product of eigenvalues, this product should be the same as the determinant of that matrix. If determinant of matrix is same as the product of eigenvalues, we can say your eigenvalues are same. One more way, you take the sum of eigenvalues, you check the trace of the matrix. Trace of the matrix is nothing but the sum of elements in principal diagonal. That is the trace. It means you can cross verify whether eigenvalues and eigenvectors are same. Then we have orthogonal vectors. We seen how to write the orthogonal vectors, how to check the orthogonal vectors. Suppose x1 and x2 are two vectors. You take x1 transpose x2 if it is equal to 0 product, or x2 transpose x1 equal to 0. If the product is 0, we can say the two vectors are orthogonal. Then we have seen 4 different methods to find eigenvectors. Not different methods, 4 different matrices are given: symmetric matrix or non-symmetric matrix, non-symmetric matrix with different root, repeated roots, symmetric matrix with different root and repeated roots. Non-symmetric matrix and symmetric matrix with different roots, the procedure is same. You will get, after using those different 3 roots, lambda equal to, in that matrix equation, matrix A minus lambda I into x equal to 0, you may find different 2 equations, maybe 3 equations different. Those 2 different equations, use their Cramer's rule and find the eigenvectors. This is applicable for both non-symmetric matrix with different roots as well as symmetric matrix with different root. The procedure is same. In case of non-symmetric matrix with repeated roots, here one fellow has asked how to decide value of k1 and k2. If the roots are repeated in case of non-symmetric matrix with repeated roots, you will get all three equations are same there if the roots are repeated. Then in that case you choose x equal to k1, y equal to k2, and z in terms of k1, k2 you will get. There are three cases. Either you choose k1 equal to k2, or means k1 equal to 1, k2 equal to 1. You don't take k1 is 0, k2 is 0. K1 is 1, k2 is 1 in case of k1 equal to k2. Or you can take k1 is 0, k2 is 1. Or you can take k2 is 1, k2 is 0, k1 is 1. Means three cases. You can take any one from these for second eigenvector. Then whatever you have chosen, you take other way. If you have chosen k1 is 0, k2 is 1, for third eigenvector you choose k1 is 0, k2 is 1. Okay, this is. Then in case of symmetric matrix with repeated roots, for first eigenvector you take different eigenvalue lambda equal to what is that different, find first eigenvector. Then second eigenvector, suppose lambda equal to that 1 1, you choose adopt same method as in non-symmetric matrix with repeated roots. Choose x equal to k1, y equal to k2. Then either you take k1 equal to k2, or k1 is 0, k2 is 1, k2 is 0, or k1 is 1. So find the second eigenvector. Then to find third eigenvector in case of symmetric matrix with repeated roots, we have to use that concept, orthogonality concept here. If the matrix is symmetric, two different eigenvectors are orthogonal. So you choose x3 equal to LMN, third eigenvector, and other two vectors already are there, x1 and x2. It means you can write x3 is orthogonal to x1 and x2 is orthogonal to x3. Using this orthogonality property, you can find the third eigenvector. These are 4 ways to find eigenvectors. Again, you can chat with me. You have any query? Only 13 students are there. So this is about eigenvalues and eigenvectors. So in next, we think about Cayley-Hamilton theorem. We will see in next class. So today we end today's lecture.